Hello guys, welcome to my YouTube channel. So in this video, we are going to do the energy tally, the amount of energy that can be formed as a result of the breakdown of palmitic acid. And if you haven't watched my previous video on the oxidation of fatty acid to the beta oxidation, then I would advise that you go and watch it so that you can know what you are going to do from here. Now, when we broke down the palmitic acid, we produced acetyl-CoA, right? So we produced how many acetyl-CoA? Produced 8 acetyl-CoA and 7 rounds, that was 7 NADH and FADHs. But now, before we get into that, let me do a quick recap so that you can see what is really going on. So we had palmitic acid. Palmitic acid was acted upon by an enzyme. Now this enzyme was called fatty acyl CoA synthetase. Now what fatty acyl CoA synthetase did was just the addition of CoA bound to a thionyl group. Then this reaction required some ATP converted into AMP plus pyrophosphate. Alright. So what did we form? We formed a pretty cool molecule here, and this one is called palmitoyl CoA. Alright, palmitoyl CoA cannot get into the mitochondrion, and therefore we had a molecule, or actually an enzyme located on the outer surface of the mitochondrion, and this enzyme is going to be called carnitine acetyltransferase type 1. So this is called CAT1. CAT1. Or now specifically we are dealing with the palmitoyl, is going to be called carnitine palmitoyl transferase type 1. So what this enzyme is going to do is very funny. It is going to, inside the cytosol, right, there is a molecule called carnitine. So this enzyme is going to replace the CoA with the carnitine. So we are going to get rid of the CoA, then you are going to add a carnitine to the palmitoyl, so that you are going to have palmitoyl carnitine. The reason why we are doing this is because palmitoyl CoA cannot get into the mitochondrion, but palmitoyl carnitine can get into the mitochondrion via the carnitine translocase, right? So palmitoyl carnitine can now enter inside the mitochondrion. Then you have our palmitoyl carnitine. But now there's another problem. Palmitoyl carnitine cannot undergo beta oxidation, so we have to replace the carnitine with the CoA. So this is going to be done by a pretty cool enzyme, and this enzyme is located to the inner membrane of the mitochondrion. Now this enzyme is going to be called CAT2. CAT2. Or you can simply call it CPT2. This one can call CPT1. Carnitine palmitoyl transferase 1, or carnitine palmitoyl transferase type 2. What it's going to do is simply going to bring in CoA, coenzyme A, then bring off the carnitine. So carnitine is going to remove the carnitine. The carnitine is going to travel out. This transporter is bidirectional. So carnitine is going to travel out into the cytosol to wait for another reaction. So that we now have our molecule, and this molecule is going to be called palmitoyl CoA. Alright, then you can now undergo beta oxidation. So I'm just going to tell you the steps of the beta oxidation. So palmitoyl CoA, there's a mnemonic of mastering the steps of the beta oxidation. So I'm just going to say, let me set a different pen here. You are just going to say O hot. O hot. Yes. So how are we going to master that? Let's do this. This O, the first O means oxidation. So oxidation. And actually it is the first oxidation. So you can just call it first oxidation, not just oxidation. So what's going to happen here? We are going to involve the reducing coefficients. So we are going to have the FADH. FAD plus, that's the flavin adenine dinucleotide, is going FADH2. Alright. Now, what are we going to form there? We're going to form acyl CoA. Right? We're going to form, what are we going to form here?
Trans delta 2 enol CoA.
Trans delta 2 enol
CoA.
Right, we're going to form trans delta 2 enol CoA. And guys, I hope you know, you saw how trans delta 2 enol CoA was looking like. Alright. Now, that's oxidation. Then let's move to the next step, which is the hydration. So hydration is the addition of a water molecule. So hydration. So what are you going to do? You're going to add a water molecule here. Let me use a different pen there. We're going to add a water molecule. Then once we add a water molecule, we are going to form a new molecule that's going to be called beta hydroxy acyl CoA. Alright, beta hydroxy acyl CoA. So this second step is called hydration, the addition of a water molecule. Right. Let's move to the third step. The third step is going to lead to the formation of a molecule called beta keto acyl CoA. Beta keto acyl CoA. That's pretty cool. Now this step is going to be called that's addition. This is going to be called second oxidation. Second oxidation. Now, hope you guys remember. Second oxidation is going to involve the reducing coefficients. So in this case, we are going to have the NAD plus is going to be reduced into NADH. Then nicotinamide adenine dinucleotide. Alright, then I'm going to the last step, guys. This last step is going to be called theolysis. Theolysis. Lysis. I'm going to lyse. Let us see what's going to happen there. Alright. So, then actually, we're going to form two products. Now, this enzyme is going to input a CoA into the beta carbon, right? It's going to input a CoA into the beta carbon. Then it's going to lyse the alpha beta bond. So we are going to form two products. We are going to form fatty acyl CoA, and acetyl CoA. Alright, guys. Fatty acyl CoA can now get back into the next round of the beta oxidation. You know it is short of 2 carbons, the acetyl CoA. Acetyl CoA has 2 carbons, so it's going to get back, but it is short with 2 carbons, or 2 carbons less. Now, when you break down the palmitoyl CoA, we formed how many acetyl CoA? Now it is 16 carbons, so we can do that again so that we can confirm with it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Alright. But you say we get rid of the acetyl CoA per every round of the cycle. So we're going to move 2. Alright. So how many acetyl CoA do we have here? We have 1, 2, 3, 4, 5, 6, 7, 8. So you have 8 acetyl CoA. And then how many rounds did we go? 1, 2, 3, 4, 5, 6, 7. So we had 7 rounds. That is to say that that is to say that we have 7. Let me just do them here. This one means 7 FADH2. Then this one means 8 7 NADH. Alright, and 8 acetyl CoA. 8 acetyl CoA. Alright, yes. Now, one acetyl CoA, now let me just show you here. This is going to move to the TCA. The TCA, right? The tetracarboxylic acid cycle or the Krebs cycle. We're going to get it. We're going to form NADH and FADH, and also we're going to produce some ATP from the TCA. But now, how many molecules of NADH are you going to produce from the TCA? You guys remember when we did the glycolytic pathway, the Krebs cycle, we formed how many molecules?
3.
We formed 3, right? So we formed 3 NADH, we formed 1 FADH2, we formed 1 molecule of ATP. Right. That's pretty cool. But now, this is from 1 acetyl CoA. Now, so we have how many acetyl CoA? We have 8 acetyl CoA. So we have 3 NADH from 1 acetyl CoA. Then let's multiply that by the 8 acetyl CoA. We're going to have 24 NADH. Right. But now, remember, we also have this NADH from the beta oxidation. So how many NADH? 7. So plus 7 NADH. So how many? 31 NADH. Alright, that's cool. Now, we formed 1 FADH2 from 1 round of the TCA, the Krebs cycle, but now we have 8 acetyl CoA. So we are going to have 8 times 1 FADH2 times 8. That's going to be 8 FADH2. Alright, but remember we also have the FADH2 from the beta oxidation. So we are going to add plus how many? 7 FADH2. So we are going to add 7 FADH2. So that's going to be 15 FADH2. Alright. We had 1 ATP in the TCA from 1 round of acetyl CoA in the Krebs cycle. But now we had 8 acetyl CoA. That's going to be 1 ATP times 8 times 8, right? That's going to be 8 ATPs. Alright. Now, let's come to the energy tally and input those values. So we have 31 NADH. So 1 NADH, let me just show this. Let me just show you. 1 NADH equals to 2.5 ATP, while 1 FADH2 is equal to 1.5 ATP. Don't be surprised to see other books or other professors telling you that it should be 3 ATP. Sometimes they use 3 ATP for 1 NADH and also 2 ATP for FADH2, but the standard way is this one. You can either use either of them, but it's okay. So we're going to multiply that 1 NADH times 2.5. So let us do that very quickly. 31 NADH times 2.5. So 31 times 2.5. That's going to give us 77.5. So we are going to have 77.5 ATPs. Alright. Then, how many FADHs do we have? We have 15 FADH2. So, 15 FADH2. I want to multiply by 1.5. Then, what are you going to get? 15 by 1.5. That's going to be 22.5. 22.5. Alright. Then we have how many ATPs? That's going to be 8. 8 ATPs. 8 ATP. Because that's going to be 8. 8 ATPs. But you guys remember, during the activation process, while we are activating the palmitic acid, we used 2 ATP molecules. So we are going to less 2 ATP. Now, let us get the total. Alright. So, that's going to put here less 2. Let's go to less 2. Right. So, we are going to have 77.5 plus 22.5 plus 8. That's going to be 108. 108 ATP. But now we are going to less 2. So we are going to have 106 ATP. Alright. That's good. I hope you guys remember why we are removing 2 molecules of ATP. Because of the activation step, we used 2. So this is the net amount of ATP that you are going to obtain from the complete oxidation of palmitic acid. Now that's pretty cool. Now you see, palmitic acid produces a lot of energy as compared to palmitic acid is from a lipid, is a lipid. So produces a lot of energy more than carbohydrate. Maybe when you are oxidizing glucose, we will have not produced such amount of energy. Now that's pretty cool. I hope you guys remember everything. They're all hot. This is just like a mnemonic from mastering the process of the beta oxidation, nitration, second oxidation, theolysis. We produced 8 acetyl-CoA, then 7 rounds. And you guys remember I told you that when you are given to break down or oxidize a particular number of fatty acids, divide it by 2, that is going to be the number of the acetyl-CoA you are going to get. For example, when you are given, for example, even 30, right? Then you are going to divide, so for example, set 30 because the fatty acid has 30 carbons. So I'm going to divide this by 2, get 15. That's so 15 is going to be the number of acetyl-CoA you're going to get. Then when you less 1 is going to be 14. So that's going to be 14 rounds. So 14 rounds resembles 14 FADHs and 14 NADHs. So that can help you with the energy time. Alright, now let's do something here. This structure you are seeing here is a peroxisome. I don't know, it's a peroxisome, right? Now, inside the peroxisome, we also do the beta oxidation just like in the normal cell, in the mitochondria. But now there's a slight difference. So suppose here we have our palmitic acid. Palmitic acid. Alright. Palmitic acid is going to get into the peroxisome. So go ahead and look. This is a palmitoyl-CoA. I'm sorry. Palmitoyl-CoA. So I will talk about palmitoyl-CoA. So palmitoyl-CoA is going to undergo the process of the beta oxidation to form. Just going to write this side to form acetyl-CoA. So this is beta oxidation. But now guys, here comes the unique thing. Remember the first process of beta oxidation? The first oxidation, the FADHs were being reduced into FADH2. So that's where we are going to see the difference. So FAD plus converted to FADH2. But now, what's going to happen to FADH2 in the normal mitochondria is going to be taken to for the energy type, no, the electron transport chain to yield energy. But now, in this case, the FADHs are going to pick oxygen molecules and some water, then it's going to be converted to hydrogen peroxide. And guys, you remember, hydrogen peroxide is toxic. It causes a lot of oxidative stress. It is a reactive oxygen machine, so we cannot allow it to stay inside the cell. So what is going to happen? We are going to have a mechanism inside the peroxisome that is going to degrade the hydrogen peroxide. So you know this is going to be done by an enzyme, and this enzyme, let me just reduce this somewhere here so that you can see it very well. So let me see this acetyl-CoA. So we are going to have the hydrogen peroxide. So hydrogen peroxide is going to be acted upon by a certain enzyme. Now this enzyme is called catalase. So catalase enzyme is going to convert this hydrogen peroxide, so let me just write here, catalase. Is going to convert the hydrogen peroxide back to its original component. That is the oxygen and water. So this process is called the detoxification. We are trying to detoxify hydrogen peroxide, which is a reactive oxygen acid, can cause a lot of oxidative stress, can cause a lot of cell damage and everything. Yeah, so that's why you cannot decide to have it in the cell. Otherwise, everything else in the peroxisome is just going to remain as in the mitochondria, apart from the degradation of the hydrogen peroxide. Now guys, we are going to go, what is remaining is just the disorders associated with when we have defects in this particular cell organelles and the processes. So for example, when we have a defect in, the first enzyme that catalyzes this reaction is called acyl-CoA dehydrogenase. Now, when there's a defect in the medium chain acyl-CoA dehydrogenase, the defect is going to be called, let me just write here, it's going to be called MCAD. Now, this simply means medium chain acyl-CoA dehydrogenase deficiency. So, when there's a deficiency of this particular enzyme, to mean you cannot break down palmitoyl-CoA into trans-2-delta-2-enol-CoA so that you can grant the beta oxidation. So to me, there is going to be accumulation of the fatty acid CoA in the mitochondria. Then significantly, you can see the effect in the liver. So when you have accumulation of this palmitoyl CoA, because remember, the beta oxidation mostly occurs in the liver and other but mainly in the liver. So we're going to have the accumulation of the fatty acid CoA in the liver, and this is going to lead to a condition called hyperlipidemia. It's a different thing. We're going to have hyperlipidemia. Right? Then the people with these, or the individuals with this particular condition also experience hypoglycemia. That matter. Hypoglycemia. You know what hypoglycemia means? That you build up amount of glucose level in blood, right? Now, so individuals with this particular condition, so this particular symptoms, always have experienced the following. Let's call them symptoms for that matter. They experience, and just combine these two. They experience vomiting. They experience extreme sleep, right? Sleep, they always sleep. Then they can have comatose. So these are some of the symptoms associated with the deficiency of the acyl-CoA dehydrogenase, right? So leading to accumulation of the fatty acid-CoA in the liver, hyperlipidemia, hypoglycemia for that matter. Then these are the symptoms: vomiting, extreme sleep, and also comatose. Then there's also another pathological disorder here. We can have the defect in the transporters that transport the palmitoyl CoA, the fatty acids inside the peroxisome for the breakdown, the beta oxidation, so that can break them down. So when there's a defect in those particular transporters, we are going to have the accumulation of the palmitoyl, the fatty acid CoA in the blood cytosol. Yeah. So this condition is going to be called X-linked, maybe it's a different one. X-linked adrenoleukodystrophy. X-linked adrenoleukodystrophy. Now you see, X-linked means it's located in the X chromosome. So to mean this thing or this particular disorder mostly affects male. So boys, boys of age less than 10, yeah. So less than 10 years. Alright, so X-linked adrenoleukodystrophy. And also, you see when there's a defect in those particular transporters, we are going to have the accumulation of these fatty acids in the body. right? In the blood, in the cytosol. So we're going to have hyperlipidemia at the same time. We're going to have hyperlipidemia. Right. And individuals with this particular defect or symptoms are going to experience, now, they are going to experience significant behaviors like, okay, they can experience behavioral defects, and call it behavioral defects. Another thing they can experience, another thing they can experience apart from the behavioral defects, they are going to experience coma. They can experience coma. Yeah, and also another thing, they can experience visual defects or dysfunction or disorders related to the sight and all those other things. So that is all about the video. We have done the breakdown for the beta oxidation, the energy tally, and this is very much crucial. You must know the amount of NADHs, amount of FADHs you are going to produce from the oxidation of a particular fatty acid. Yeah, then you're going to calculate, of course, you know, NADH is 2.5 ATP per molecule of NADH, FADH is 1.5. Do the energy tally for palmitic acid is going to be 106. This is the net amount of energy produced. Then for the peroxisome, now this is a peroxisome. We did the beta oxidation for the peroxisome because it is kind of different from the mitochondrial. And you see, you are going to involve the hydrogen peroxide, which is a reactive oxygen species, and it is very toxic, so you can't allow it to accumulate to the body. So you are going to involve the enzyme catalase, well, but in the breakdown of the hydrogen peroxide into oxygen and water, which are less toxic. Then, of course, you have the disorders associated with the defects in the transporters of the peroxisome, and also the deficiency of the acyl-CoA dehydrogenase. Guys, we are through, and that's it for this video. If you found this video helpful, please subscribe to my YouTube channel, comment, and like. Thank you so much, and let's meet in our next video. Please stay tuned so that you may know more about metabolism and everything that occurs in our body. Thank you.